Okay, thanks.
Okay. I think I need to check my cell phone from time to time in case I do it too long or too short. So my topic is about the spreading processes on the metapopulation network with a special mobility rule. We come from different backgrounds, I think. So it's better to start it from the scratch, even though some materials are naive to the audience. So the metapopulation network has two levels. On the macroscopic level, it is just a network where each node represents a habitat. For example, it can be the college, can be counties, cities, or states, just depending on our research scale. And each pair of nodes, sometimes we call subpopulation, are connected by some physical method, just like maybe railway, maybe airlines. And if we zoom in one subpopulation, and we can see so many individuals, those individuals are well mixed within each subpopulation. And that means that each pair of the individual interact with each other with even probability. And in the meantime, those individuals can diffuse into the adjacent neighbor along those edges. We are going to talk about the epidemic spreading on the metapopulation network. So which means that those individuals fell into one of the category, infectious or susceptible. The infectious individual will propagate the disease to the susceptible individual with a fixed infection rate beta. And in the meantime, those infectious individuals will recover from the disease with a fixed rate mu. Okay, my core case is say node2vec mobility. Lots of people ask me, say, what is node2vec before I gave this talk. So maybe I just started from some naive examples. It comes from the computer science. When the computer scientists talk about the graph embedding. An embedding is not something new in mathematics. Usually speaking, an embedding is just a map from our target space to the Euclidean space. For example, if we talk about colors, we have a panel of colors, and for those colors here, I just enclose it by the dotted white lines. In our natural language, we can say, well, they are dark blue, medium blue, and blue. However, we know that there are infinitely many colors. The color spectrum is continuous. And our natural language is something discrete. So it is insufficient to depict all the colors by our natural language. A clever method, also very successful, is the RGB representation, which means that we map each color into a three-dimensional Euclidean space, such that each color corresponding to one point here. So it is the most simple embedding or representation in mathematics. The node2vec embedding actually comes from the word embedding. Word embedding considers, say, well, our target space is a bunch of words from articles, from literatures, and somehow we need to embed it into a Euclidean space. Mathematicians may prefer to say, well, suppose we have 10,000 words and we just embed it into a 10,000 dimensional space. However, we know that it is impossible for the downstreaming tasks in the application of fields because of the curse of dimensionality. So actually, what we are really want to find is not something, not only an embedding, but a feasible embedding, such that it is embedded into a lower dimensional space. So because of that, I think about in 2013, the computer scientists figured out a method which is called word2vec, which means that they try to embed those corpus into a neural network, such that in the end it generates an embedding here. It is an example, say, embed those words into a two-dimensional Euclidean space. Here, as we can see, those locations are clustered together, and those animals clustered together, and pronouns clustered together. The so-called word2vec is one of the most successful word embedding strategy. And because of this, when computer scientists consider the node embedding, one strategy is that they just use this frame and they say, well, we have a graph, and how could we generate some context? Or they say we release some random walker. One type of the random walker is called node2vec. So the random walker travel along those edges, and it has a trajectory. We just treat this trajectory as our sample, and we feed those trajectory into the neural network, and in the end, it generates a node embedding here. So strictly speaking, in machine learning or natural language process, when people talk about node2vec, what they really say is about not only the random walk itself, but also the neural network, also about some acceleration in the embedding method. However, today I just want to talk about mathematics. So the node2vec I'm going to talk about, it's just a random walk. We do not care about what is the neural network, what are the algorithm. We just consider random walk. Okay, so let's give a formal definition. What is node2vec random walk? I think all of us should be very familiar with the simple random walk, which means that suppose we can see a fraction of the network here, and if we have a particle located at the center node, and in the next unit moment, it will migrate to one of its neighbor, right? So for the center node, it has 4 edges connected to this node. So for each direction, we just assume the probability is 1 or 4. So it is the, suppose a random walk satisfies this mobility, we just say it is a simple random walk. The node2vec random walk is something different. It not only cares about where it is, but also cares about where it came from. So the node2vec random walk say, well, still our particle is located at the center node. And in the previous moment, it was located at the, let's assume it is located at the lower left corner node. So it has a trajectory like this. In the next moment, it can go backwards, means return to the previous node with a weight B, or it can go to a common neighbor. I say it is a common neighbor because the upper left corner node is not only a neighbor of the center node, but also the common, but also the neighbor of the lower left corner node. Okay. Suppose it goes to the common neighbor, it has a weight C. If it goes to some other nodes, we just assume this weight is equal to +1. So by this description, we can write the normalized transition probability P like this. And a special case is that if the backtracking weight and the weight visiting common neighbors are both equal to 1, this node2vec random walk just reduced to the simple random walk. If we draw a Venn diagram, we can say, well, the largest site is the all the possible random walks on the graph, and the node2vec is a special case, and it contains the simple random walk as a special case. So here are some questions and motivations I need to explain. Why I'm going to consider the research by mathematics, not the data-driven research, because just after the breakout of COVID-19, I think lots of the research was done by statistics or machine learning. Well, the reason is that the data-driven research sometimes can be misinterpreted. For example, if somehow I get some data in the United States and I get some conclusion, but how could this data is fitted in UK or in Germany? Well, we know that in different countries, people have different culture and may have different mobility rule. So just use this conclusion directly may be not suitable and sometimes leading to the wrong result. And the second reason is that simple random walk is insufficient to depict the human mobility. Here on the corner, there are some references to point out this issue. And also intuitively, just take me for an example. My lifestyle is very simple, just say from home to school and from home, school to home. So simple random walk is not a good model, at least for me. I think if you wanna use a random walk to depict my mobility, it should be a backtracking random walk, right? So our question is that, well, how this node2vec mobility or node2vec random walk affects the epidemic threshold? I will explain what is epidemic threshold in the later pages. Okay. Sorry, just I'm having a talk. I'm sorry. Okay, so let's where I am. Okay. Before we are doing the mathematics, let's have some notations in mind. And so we know that the node2vec random walk is not is a random walk. Not only cares about where the particle is, but also cares about where it came from. So actually, it is a second order random walk. Theoretically speaking, there exist some results for the higher order random walk in mathematics, but those theoretical results sometimes are very hard to use, and it leading to a very complicated explanation. So so our strategy is that try to reduce this second order random walk into a first order Markov chain. What we do is say to consider the memory network. That is to say, instead of considering all the nodes on the metapopulation network, we just consider all the directed edges. For example, if I wanna show a particle was from the lower left corner node to the center node, I just use this black arrow to show this mobility, and the arrowhead pointing to a node where the particle is. And in the next union time, it can go backwards or go to the adjacent, go to the common neighbor, or it goes to some other nodes. I just use the blue arrows to show all the possibilities. And here, by this transformation, we can figure out, well, it can be a first order Markov chain, and we can write down the transition probability matrix like this. Here it is a small notation, say, well, let's say for arbitrary directed edges, I use E sub I of 0 to show the initial node, and E sub I of 1 to denote the targeting node. Okay. So okay, with all these note, sorry, some other notations. And if we zoom in one subpopulation here, we can see so many individuals if we consider the human being. And I use the green color to say the individuals who are susceptible, and red colors to show the individuals who are infectious. And the green circles means that the individuals are coming from the, say, lower left corner node. So I mean, the green circles means those individuals along this black coming along this black arrow. And for those triangles, no matter it is infectious or susceptible, we just assume that they coming from some other nodes without pointing out where it come from. So the susceptible individuals migrating from the lower left corner node, let's assume those numbers is equal to rho sub s comma I. For the infectious individuals, I say those numbers are rho sub I comma I here. Okay, so with all this notation in mind, and now we can set up our equation. The master equation to depict this dynamics can be given here. On the left-hand side, it is the rate of change for the susceptible or infectious individual, and on the right-hand side, just take the first equation for an example. The first term means the infection events in the targeting node, and the second term means the recovery events, and the third term accounts for the number of individuals diffuse out, and the last term represents the number of individuals who diffuse into the subpopulation. A similar explanation can be made for the second differential equation. And actually, even though I only write two equations here, but we know this I can be integers from 1 to n. So actually, this it is an equation system. And our question is that how to find the epidemic threshold for the node2vec mobility. The epidemic threshold is a value. I mean, we consider as an S model. So the epidemic threshold is a value where if the infection rate is smaller than this value, and then we can see no pandemics. If the infection rate is greater than this value, as t goes to infinity, eventually we will see a fraction of individuals who get infected in the end. Such a value is important in epidemiology, and we are going to try to derive it in these slides. And the actually I skip some details here for this differential equation. Okay, let me see how to say that. First, we should figure out what is the stable point on the phase space, and this stable point can be derived from this from the stationary probability of the node2vec mobility, and we can consider the linearization at the stable point, and we get a Jacobian matrix J. The mathematics tells us that if the real part of the eigenvalues are smaller than 0, such a stable point is asymptotically stable. Otherwise, it can be neutrally stable or unstable. So the matrix J, the Jacobian matrix J, is denoted by a formula here. And it has 4 terms. The first term actually is completely determined by the topology of the network, which means that if a network is given, and then the first term is given. And on the second term and third term, the matrix I is just the identity matrix, and mu is the recovery rate, I is the diffusion rate. And the last term is the transition probability matrix. We know that the node2vec random walk has 2 parameters, backtracking parameter and the weight visiting common neighbors. So actually, it is a matrix function in terms of B and C. So in the end, we can say our epidemic threshold beta C is a function in terms of 3 variables, B, C, and DI. So since it is a function in terms of 3 variables, to visualize that, we just try to fix one variable to be positive 1 and change the other 2 variables and see how it evolves over those variables. And we considered the scale-free network, or more precisely say the Balabasi-Albert model. If we fix the diffusion rate to be positive 1, and we can see that the epidemic threshold is large if it has a smaller B value or smaller C value, which means that if the individual less frequently backtrack or less frequently visit the common neighbors, in those cases, epidemic threshold increases. or you can also say the epidemic spreading is suppressed. Look at the second and the third panel, we can see that, well, the diffusion rate actually is has a stronger impact over the backtracking weight B and over the weight visiting common neighbor C here. And our observation say the diffusion rate can suppress the epidemic spreading is consistent with some other research, just like Matsuda in 2010 and also Gomez-Gardenis in 2018. And so also from those figures, we can claim that the impact of those parameters on the epidemic threshold satisfy an inequality here. So we just take an example for the Balabasi-Albert model. And actually, we can also test these results for some other model networks. For example, the first network is a benchmark network with a strong community structure, and the second and the third networks are empirical networks. One is the U.S. airport network, and the other one is a Colombian network. So for those networks, we can get similar results, and we also test some other networks, and the results are similar. So one may ask that whether it is true for arbitrary graphs, and actually, unfortunately, the answer is no. We can construct a network where the epidemic threshold is independent of the choice of those node2vec parameters and the diffusion rate D. It is the so-called vertex transitive graph. To explain what is vertex transitive graph, I think I just started from the scratch to talk about what is isomorphism. So the isomorphism of graphs, let's say G and H, is just a bijection from those vertex sites. Let's say suppose phi is the bijection, and if this bijection satisfies that two vertices, let's say U and V, are adjacent in G, it is also adjacent in the set H. Then such a bijection is called isomorphism. Suppose these two networks are the same, let's say G equal to H. Isomorphism is called automorphism. Some very famous isomorphic examples, in the meantime, it is non-trivial, is the so-called Peterson graph. For example, here is a network with a regular network with 10 noses, and we have the other two networks, and actually we can show that all the three networks are identically the same, which means that they are actually the same network. The only difference is that they have different layouts. Also, there exists some non-isomorphic examples. The first figure is still for the Peterson graph, and the second one is the Cayley graph for the dihedral group D5. Actually, there are so many methods to show they are non-isomorphic. A simple observation is that, well, for the second graph, we can find a cycle of length 4. For example, it goes from the node here and just through these edges and goes back in the end. So it has a cycle of 4. However, for the Peterson graph, it only has a cycle of 5. So that is why they are non-isomorphic. Some other observation may be useful. For example, the first graph is non-Hamilton, but the second one is Hamilton. So anyway, however, in general, how to find two graphs are isomorphic, or how to find non-trivial automorphism is an NP complete question. So I think there is no general algorithm to find it out. Now I can talk about something I want to say. What is vertex transitive? So a graph G is called vertex transitive. Suppose its automorphism group acts it on transitively. It sounds very tough, but intuitively it means that you choose arbitrary pair of nodes, and then you can always find an automorphism to send one node to the other. A very simple example is this extended ring network, or maybe you call it is Voss-Strogais model, but here without rewiring. Such a network is the vertex transitive graph. And actually, we can show that the epidemic threshold beta C for the vertex transitive network is a fixed value, which is independent of the choice of the node2vec parameters and independent of the choice of those diffusion rates. So the strategy of those proofs given like this. Here I just show this result for the extended ring network, or you say for this Voss-Strogais model. Actually, this proof can be completely applied to arbitrary vertex transitive graph with just small, just with very small amending, and it can be transplanted. So the sketch of the proof goes like this. First, we recall that the epidemic threshold is given by a formula here, which means that we need to figure out what is the Jacobi matrix J. And the first step is that we are trying to find a reasonable order for the direct edge space of the vertex transitive graph, such that we can decompose the matrix J, or I should say rewrite this matrix J into a block circulant matrix. That is to say, J is equal to the block circulant matrix of those small matrices. And the mathematics tells us that suppose a matrix is block circulant, then its eigenvalue can be decomposed into the eigenvalues of several small matrices. I say those small matrices are matrix H. And now we can rewrite our epidemic threshold in terms of a formula here. So actually, from the Jacobi matrix J to the matrix H here, it seems that we haven't simplified too much, because here we have to consider n small matrices, right? It sounds still pretty difficult. However, an important observation is that suppose we can draw those Crosscurrent circles for those small matrices. And here I just use the blue circle to show to denote the to denote one of the Crosscurrent circle for matrix H0. And I use yes. Oh, okay. Sorry. So I just use the blue circle to show one of the Crosscurrent circle for matrix H0, and the white circle to show the one of the Crosscurrent circle for Hj, where J is not equal to 0. And we have some observations. The first observation is that those white circles always have a smaller radius than the blue circle. And also the center of those white circles are always on the left of the blue circle. So actually, intuitively, it means that suppose our blue circle is on the left-hand side of those vertex axes, and then all the white circles should also located at the left-hand side of those vertex axes. And we can show that suppose the infection rate is smaller than the constant mu over rho, and we can say that in this case, I say the blue circle has no intersection with the vertical axis, and so all the other white circles. So in this case, the stable point actually is asymptotically stable. Suppose our blue circle is tangent to the vertical axis. In this case, our infection rate is equal to mu over rho, and we can find out in this case, we have unique eigenvalue equal to 0. In this case, the stable point may be neutrally stable, maybe asymptotically stable, but actually it doesn't matter. The key point is that suppose our beta is greater than this value, we can always find a positive eigenvalue lambda here, which is equal to beta rho minus mu. So which means that in this case, the stable point is unstable. So that is why we can claim that we do not have to see all the other circles. We only look at the blue circle, and then that will be done. In the end, we can simplify our epidemic threshold in terms of a very simple notation. Here we only need to care about the matrix H, where it's just a 4x4 matrix. So no matter how large this network is, how many nodes there is, in the end, we only need to consider a 4x4 matrix, and that is the conclusion. So here it is our proof for the extended ring network. Suppose we have a arbitrary vertex transitive graph, we can always use the similar strategy and show the epidemic threshold is a constant here. Finally, let me summarize our contribution. First, we point out that the epidemic threshold increases or the epidemic spreading is surprised. Suppose we have smaller backtracking weight, or the weight visiting common neighbors is small, or maybe the diffusion rate is larger, and also we can compare the impact of those parameters. We say the backtracking weight is the weakest one, which is smaller than the weight visiting common neighbors, which is smaller than the weight of diffusion rate. And also in the end, we showed that the vertex transitive graph has a constant epidemic threshold, which is independent of the choice of those parameters. Our research has some limitations. For example, let's recall the expression for the epidemic threshold. Here, actually, we can see it is a very tough notation. The matrix J has 4 terms. The first term is just a symmetric matrix, actually, and the second term is also symmetric. The third term is symmetric. Unfortunately, the last term is asymmetric. And usually speaking, there is no reasonable way to diagonalize this matrix or try to transform it into a product of symmetric matrices. So that is why we have to conduct some numerical research sometime. Well, just because of this asymmetric property. And some other possible applications for the node2vec may be considered in the nodes ranking or community detection. We know that so one of the most famous ranking method is the PageRank. So actually the PageRank just uses a simple random walk, right? We can expect what kind of the usage can be applied in node2vec ranking algorithms. And also there are some community detection algorithms which use the random walk algorithm. So maybe node2vec is suitable for those questions. Okay, I think that's all I want to say today. And sorry, I just pretty nervous and make this talk to be very lame. If you have any questions, I'm very happy to answer your question.
Thanks for your very interesting talk. So do we have any questions from the room? Okay, Renaud, please.
Yes, so I was wondering, so here you have these parameters in your model. Do you have some insight on what would be the right values coming from mobility data? Do you know what would be realistic values for those parameters?
Sorry, Professor. I cannot hear you very clearly.
So you have parameters for your random walk model, right? And I was wondering if you had any data that could give you an indication of what would be realistic values for these parameters in order to model human mobility.
Sorry. Could you please just repeat your question again? Because I really have a hard time to.
No problem. So I tried it out. So you have 3 parameters for your random walk, right?
Yes, we have 3 parameters. Let's say B, C, and D.
Yeah. And so what I was wondering is, do you have do you have information from data that could help you to know what would be realistic values of those parameters?
Actually, unfortunately, I haven't tried this on data yet because I have no access to the real data. Say how to from the real data to the maybe by statistical method or likelihood estimation to estimate those parameters B, C, and D. Unfortunately, I haven't do this yet. I only consider some empirical networks and see whether it has similar results on the model networks.
Okay, thanks.
Thanks. Do we have other questions? Or from online? Okay, I don't see any questions. So I have one. Can I ask why you call this random walk node2vec random walk?
Why I convince the node2vec random walk?
No. I mean, why you call this network node2vec random walk?
Okay. Sorry for my misunderstanding. Actually, well, it's just maybe I just want to use this terminology because I don't want to create some new terminology, say a second order random walk or something like that, because in node2vec embedding, the key point is that they just try to find a second order random walk such that based on this random walk, it generates a trajectory, and they feed this trajectory into the neural network and so on. So all the parts here are called node2. All the parts above are called word2vec. So the only difference is that how they generalize those samplings. So actually, the key point for the node2vec is that they proposed a sampling strategy such that it generates a feasible data set or a feasible corpus into the neural network, and in the end they get the node embedding. So actually that is why I call this random walk is node2vec. No special reasons.
Okay, right. Thanks.
Thanks.
So I don't see any questions from the room, also online. Yeah, I see one question in the chat.
Yeah.
So
I will type out my question.
I can speak it out. So how did you measure the relative effects of various 3 parameters?
Okay, thank you for I can see your question. Okay, thank you. Actually, some other people also asked me this question before. Why for the diffusion rate? I like its range is from 0 to 10, and for the backtracking parameter and the weight visiting common neighbors to say from 0 to 5. Actually, this choice is somehow arbitrary. I mean, for B and C, actually it is compared with the baseline +1. I mean the positive one is the weight visiting some other nodes. So here I do not want to make this B and C to be very crazy range, say from 0 to 100, from 0 to 1000, something like that. So because we have a baseline weight which is positive 1 here, so just try to make it into a somehow reasonable scope. However, the diffusion rate is something different. So no matter this random walk is node2vec or simple random walk, the diffusion rate always exists. So it is a value, can say from 0 to positive infinity. So here that is why I artificially to make it into a different range. I just try to also remember myself that this B and C are in the same row. However, the diffusion rate D is in another row. So one is account for the, so parameter B and C accounts for the bias of the mobility. And parameter D explains the strength of the diffusion out of the subpopulation. So here it is my answer.
Okay. Yeah. Thanks. Thanks for. I guess that's the end of the talk. Thanks for your talk again.
Thank you so much.